I wish you a very good morning. My name is Christopher Voll, and I have the strange dual task of both welcoming you here to the research program on combinatorial methods in enumerative algebra, as if I were the host. Of course, I'm not. I'm a guest. I'm a guest at the ICTS, and I enjoy my stay greatly. It's a great honor to be here, to be back in India, in Bangalore. Yeah, let's see what we do. We are here as part of this research program. This research program has a number of organizers, and I think the first thing I should make sure is that you know who these organizers are. So I see Pooja, Singla, Uri on. If you just stood up, then people could actually put names to your faces. Pooja, Uri, there's Amri somewhere. Amri is here, and there is Angela somewhere here, and there's Christopher somewhere here. Okay, so these are the 5 organizers. Last night I went for dinner, and I struck up a conversation during which I was asked what I was doing here, whether I was lecturing, and I said no. I think I quite clearly said no. The web page says otherwise. The web page says that there are 6 lecturers. I'm one of them on the web page, but I got off lightly, so I only have to give 1 lecture apparently, as long as this lecture gives an overview of the program. So my task and pleasant duty is to give you an overview of the program, or rather of some ideas that led to some aspects of this program. There will be lecture courses by Angela Carnevale, Benjamin Klopsch, Josh Maglioni, and Amri Prasad, and Tobias Rossmann during the first week of this program. They are scheduled in slots that are published on the webpage, and the webpage we keep up to date. What I want to do today is I want to just draw a picture, maybe in which some of the topics or themes that are developed in detail in these courses play a role in the research that I care about. Yeah, combinatorial methods in enumerative algebra contains as a title a number of terms which are at least ambiguous. Yeah. So maybe at the end of this lecture, if you have some ideas why these 4 terms come together in this shape, that would be a success. So sometimes in my line of work, I get on my desk a bunch of numbers, and I have the pleasure and the duty to make sense of these numbers. So for example, these numbers could come as sequences. And at some stage, there's the famous ... Maybe a machine produced these numbers, indicating that there could be many more numbers if I had the strength or the computing power or the skills to produce more numbers. But this is already more than enough to make me open the brilliant OAIS, the online encyclopedia of integer sequences, and try my luck entering these numbers, hit enter, and be surprised that there are 48 entries that start with this sequence. But the very first one is A000203, which tells you that you might be looking at the beginning of the divisor sum function. The divisor sum function is an arithmetic function that you might well have seen as or taught to your undergraduate students, depending on your circumstances. So sigma n for an integer n is defined as the sum over all the divisors of this integer n. And if you ever saw this in a elementary number theory course, chances are that your lecturer will have discussed with you what to do with the infinitude of these numbers. Yeah, indicated here, these are not finitely many numbers, these are infinitely many numbers. And chances are that she would have advertised putting these numbers as coefficients of a suitable generating function. And this is something that we also want to do in this in the coming 2 weeks. We are given numbers which come from enumerative algebra, whatever that might be, and we put them in the right kind of generating function. Now, a function like the divisor sum function is a prototypical example of a multiplicative function. So this function is multiplicative over co-prime factors. And that is one reason, maybe the prime reason, why the right kind of generating function to make sense of these numbers as coefficients might be the Dirichlet type generating function. So a Dirichlet type generating function is a formal infinite series indexed by the natural numbers, and the summands are n to the minus s, weighed, if you want, by the numbers that you care about as coefficients. Yeah, so we might define this function of a complex variable s in this form. And I called it a function. Well, it's not a priori obvious, I reckon, the way I write it, that this actually defines a function anywhere on the complex plane, but it does. And an exercise in elementary number theory is that this function here can be expressed as a product of 2 copies of the Riemann zeta function, one shifted a little bit. So a fun fact exercise on the level of this elementary number theory course that I imagine is that this is the product of the Riemann zeta function times the Riemann zeta function shifted by 1. So zeta s is the Riemann zeta function. It's the Dirichlet type generating function, if you wish, for the constant series, constant sequence 1. And of course, the Riemann zeta function has a lot of reasons to be being one of the most studied functions in the world, presumably. One reason is, and for that you don't need to crack a millennium problem, is that this infinite sum is also an infinite product. Yeah, so it's defined as a sum over the natural numbers, but it turns out also to be a product indexed by the prime numbers. This is effectively reflecting unique factorization of these natural numbers as powers of primes. And doing this allows us to kind of concentrate on individual primes and reap the benefits from the fact that for a fixed prime, this factor here that we have is a rather simple function. It's simply 1 over 1 minus p to the minus s. You will agree that this is one of the simplest rational functions in p to the minus s I could write down without writing down a polynomial. Yeah? So this is some basic stuff about the Riemann zeta function. And knowing this, and I reckon is enough to establish this. One way to do this now is to just do this kind of prime by prime and write down the more or less obvious formula for the number of the sums of divisors of a prime power. Yeah? Okay, that's all very well. If you read in A000203 in the online encyclopedia of integer sequences, further down, the good thing about this website is it doesn't give you one definition of a sequence, it gives you loads, dozens in this case, literally dozens of interpretations of this sequence as solution to various different looking counting problems. And I would like to highlight one of these. Fact, which we're going to prove. This number, sigma n, defined as the sum of divisors of n, is also a cardinality of a set, the kind of which will keep us busy the rest of the week, maybe also in the next week, sigma n is the number of subgroups H of the free abelian group Z squared whose index in Z squared is n. Yeah. So on the left-hand side, arithmetic function. On the right-hand side, you would agree that this is now the solution to a problem in enumerative algebra. Yeah. Why is that? Why is that? Fun fact has a simple proof. Okay, so what are we counting here? We are counting subgroups of, I said, the free abelian group of rank 2. If I must, or fancy, I can choose generators for this Z module, free generators E1 and E2, say, and doing this has a number of advantages. One of them is that I can represent generators of this subgroup, which by the elementary divisor theorem I need 2 of. I can represent through a 2x2 matrix. Yeah? So having chosen this basis allows me to identify H with a 2x2 matrix in which I record the coordinates of 2 generators of H with respect to this basis. And I can do this in more or less clever ways. I can do this, for example, in the following sense. I can represent this subgroup by a 2x2 matrix which is in Hermite normal form. H and F I will use for matrices in Hermite normal forms. Just to remind you, what does that mean? That means it's an upper triangular matrix. Of course, you could convene otherwise, but for me, it's an upper triangular matrix with diagonal entries, zeros in the southwest, and crucially, in the ij entry, I choose representatives of the integers modulo d between 0 and d minus 1. So I put a star here for an arbitrary entry which is between 1 and d minus 1. Okay? Why would I do this? Well, if I do this, little exercise, also elementary, shows you that there is one and only one such matrix that represents H. So the problem of enumerating such subgroups is now the same as enumerating such matrices, and now you see why I put on the diagonal entries not simply numbers A and B. I wrote them as D and N over D. Yeah? So the determinant of this matrix here is obviously N, and this is the index of this subgroup is the determinant of this matrix. And the way I wrote it down, I think, makes it obvious that this is the same. Yeah? So for any D, I have D choices to fill up that star, and that is then just bringing us back to the definition of sigma n. Okay, so let me introduce another term for this quantity. So let me write this as an of z square. Why would I do this if there's a perfectly good name for this already? Well, one purpose is obvious, right? I mean, I would like to maybe replace one day this 2 by an arbitrary integer d, and maybe someday, like today, in an hour's time, Benjamin will introduce us to the problem of subgroup growth. So we might want to study questions like this, trying to understand the number of subgroups of finite index in a group for groups that are even wilder than z squared. Yeah, so that's that leaves us open here an inroad into subgroup growth. There's another thing that, of course, we might do at this stage. We might say, okay, now we understand subgroup. Well, now we can enumerate these subgroups of a given index. What else do we do with these groups? Well, we leave pretty much everything that's aside that's interesting about these groups. I mean, of course, they are rank 2 as well. What could there be interesting? Well, this index here, of course, is the size of the quotient group. So Z squared modulo H is a finite abelian group. And our undergraduates learn that this finite abelian group is a direct product of its pseudo P subgroups. So I can write this as a direct sum indexed by the primes. And for each prime here, I have a P group, a finite abelian P group. Let me write it as Cp to the lambda P, where lambda P is a partition that depends on the prime P. I will drop the dependence on P here, if you allow me. So lambda 1, lambda 2 is a sequence of non-negative integers which are non-ascending. Surely Josh will have his own notation for partitions. Let me write P2 for the moment for the set of partitions of at most 2 parts. So one way to deal with this partition is to write down its Young diagram. Now we're entering, I reckon, definitely combinatorial terms. People who write Young diagrams are combinatorialists, aren't they? I reckon, to some degree at least, yeah? So you remember the Young diagram of a partition is just the array of boxes drawn in the right way, and what the right way is depends on whether you're educated in France or in England. So one of these ways is to arrange it horizontally, so that here we draw lambda 1 boxes in the first row, followed by lambda 2 boxes in the second. And yeah, you might now look at this question again and not be content with ignoring essentially the finer structure of this group. You might want to keep track of the partition that you associate, or the partitions, yeah, you get one for each prime P, the partitions that you associate with this group H. So we might refine this, and this is in fact something we do want to do. And for this, yeah, we will have to, one way to think about this is to have another look at this Hermite normal form matrix. And this matrix has the advantage of telling you something at first glance, and that is the determinant. Yeah? So that n is the determinant here is obvious. In order to understand the associated partitions, we need to look a bit more closely, and we need to do a little bit of arithmetic. Yeah? But before we do this, let me pick up something that I said en passant a couple of minutes ago. I said that sigma n is a multiplicative function, yeah? Which means that if n is product indexed by the primes p to the EP, then sigma of n is nothing but the product of the sigma p to the EPs. Yeah? And for this reason, I might want to concentrate now for a fixed prime on the counting problem that we rephrased over there for n a prime power. Yeah? And if we do this, then this matrix in Hermite normal form I can rewrite a little bit. So there are lines that we mustn't cross, yeah? Just like in real life. I'm not supposed to write on the left of this. And I'm not supposed to write too high either, yeah? But if I write here, that's admissible apparently. Very good. So let me write a matrix in Hermite normal form again. And now let me not bother so much about the D and N. So let me just write this matrix in the form P to the F and P to the E on the diagonal. Yeah, so we are also free, of course, to multiply the rows of this matrix by units. And if we do this over the p-adic integers, we have essentially reduced to the fact that we have prime powers on the diagonal. And yeah, here where I wrote the star over there, let me write, okay, that star is some integer that I may choose between 0 and p to the e minus 1. And I could write it, couldn't I, in the form p to the g times u, where u is a unit modulo p to the e. Simply I just take out the p-adic valuation, so to speak, of u, and I'm left with a unit here. And why should I do this? Well, I might do this in order to write down the associated partition with this subgroup H. Yeah? So H corresponds, or is given by this matrix, and I might want to write down the associated partition. The associated partition tells us essentially what the two elementary divisors of this matrix are. The smallest one, arguably, is G. So I got G boxes here, and yeah, what is then the largest elementary divisor? Well, that is whatever it takes to make this matrix determinant P to the E plus F. Yeah, so I have E plus F minus G as lambda 1 and G as lambda 2. Okay, so a closer look at these matrices, zooming in finer on these matrices allows us to extract additional information. And that's very much something we would like to do. Just switching off this microphone is not an option, yeah? So I need to have this on all the time anyhow. I think I could fill this room, but maybe not YouTube with my voice. Okay, I'll keep it on. Good, so Joshua will take us to a connection between lattice counting problems, lattices as in subgroups in free abelian groups like this, with a specific view on finer structure of the associated matrices. Benjamin. Please. Please, yes. Why doesn't F win? F is 0. Who's killing whom? Okay, there is an F. And a 0, yes. I don't want to see what? Yeah, I get a quotient. If F is 0, then so if F is 0, yeah, then what happens? Then yes, they could be. So I could have P to the E and P to the G here, yeah? Ah, I see. Okay. Why does? Thank you, Benjamin. Why should G win? No, it doesn't. The minimum wins. Yes. So the minimum of E, F, and G wins. Thank you. And up here, whatever I need to make this E plus F minus the minimum here wins. Danke. Glad I allowed questions. Very good. I might not hear if you have further questions. Please just ask them. Yeah. Good. I said earlier on that I see this as an instance of an answer to the kind of questions that are raised in subgroup growth. So let's look at this in the just obvious next generalization, so to speak. Let me replace the z square in the example over there by a general number n. N is not so good. Let's make this a d. So let me look at the group G is z to the d, and let's now turn our attention to the number of subgroups of index n in z to the d. Number of subgroups h in z to the d, whose index is n. Now, just as we proved this fact over there, we might, I think, prove that this formulae here generalizes in the most direct way you could imagine. I mean, let's look at this again. I represented subgroups by matrices in Hermite normal form. essentially, I can now think of as when the index grows as these numbers on the diagonal to grow pretty much independently. Yeah? And one of these entries here growing gives us this factor zeta s, and the other factor growing here gives us this factor s minus 1, because it doesn't grow on its own. When it grows, it creates a kind of space for entries in here that don't affect the index. So pretty much along these lines, you prove the following proposition, which is one of the archetypical results, preliminary results in subgroup growth. The sum over a n z to the d, n goes from 1 to infinity, n to the minus s. This is what some people would call the subgroup zeta function of z to the n, and I'm sure it turns up in some form in Benjamin's lectures. D, yes, thank you, sorry, D. So it's the subgroup zeta function. I should say subgroup because there will be many variants of this function. Tobias will tell us about submodule zeta functions. I'm sure about ask zeta functions. There'll be representation zeta functions in Benjamin's lectures. So let's make sure we know what we are counting here. We're counting the numbers of subgroups. The subgroup zeta function of the free abelian group of degree d of z to the d is this, and what the proposition would say is that this is the product of d copies of the Riemann zeta function translated by 0, 1 up to d minus 1. Yeah? And by the Euler product, I should have given this the name that the world knows it by, Euler product decomposition of the Riemann zeta function implies immediately that this function here has an Euler product indexed by the prime numbers of rational functions that are very much like this here. I just have d of them and not 1, and I shift each of them a little bit. Let me introduce at this occasion an abbreviation that many people in the field use very often. They write t, either little t or capital T, whenever they see p to the minus s. So p to the minus s is something like a variable-like expression. Yeah? So s is the complex variable, but I want to treat p to the minus s as the variable expression. And with this notation, the denominator of the Euler factor here reads 1 minus t. That comes from the Riemann zeta function. Yeah? That's what we have here. Shifting it by 1 gives me a 1 minus pt, and all the way down I have 1 minus p to the d minus 1 t as the last factor. Yeah? And again, of course, how could it be differently? The Euler factors are rational functions in this variable t, and we didn't talk about the dependency on the prime very much. I just discussed the general case down to the case of prime powers. But of course, these factors do depend on the prime p. But they depend on the prime p in a very mild manner. And certainly in Tobias' lectures, I expect to learn something about how these things could depend in general. Such things could depend in general on the prime p. So let's just observe here, there's a mild dependency on the prime p, without getting into details about what mild actually might mean and what its antonym might be. Right, I would want to stop the general waffle and give you something a little bit more precise about what, from my personal view, might be 3 recurring themes in this course. And I just wonder where is the best occasion to create some space. And maybe it's the list of lecturers that is the best place to create space for general themes. Yeah, so here are some aspects of the bigger picture that I find particularly interesting. So general themes that come up in this circle of ideas over and over again. So a general approach or a method, if you want, is to harvest data, interesting data about algebraic objects or families of objects in Dirichlet type generating functions. This is often the weapon of choice, certainly for sequences that don't grow too fast. Yeah, I said I didn't discuss really why this is actually a function, at least at for some complex numbers. It is because the divisor function grows at most polynomially. Yeah? Another reason is, and that we exploited certainly here, is that if the function that gives us these numbers is multiplicative in some sense, Benjamin will discuss senses in which it is a bit more subtle than in the sense of elementary number theory that I reproduced somewhere over there. The infinite sum that we write here has actually an infinite product indexed by, let me put primes in inverted commas. So what we've seen here was a factorization indexed by the primes in the integers. If you take a number theoretic perspective, these are the non-Archimedean places of the number field Q. And we certainly encounter sometimes Euler products that are indexed by non-Archimedean, but also sometimes Archimedean places of number fields. But let me say primes. So this zeta function that encodes algebraic data turns then out to be an Euler product over local zeta functions. And something that is often true, something like a meta theorem, if you allow me this term, meta theorem, often these local zeta functions, Z, P, S, are rational functions. Rational functions, for example, in this situation we have seen this. Yeah, so there are rational functions here. In this case, we actually see a rational function in T, whose coefficients, if you think about it as a rational function over Q, depends in a polynomial way on P. But so often they are rational functions in T, and again here I'm brushing under the carpet that in interesting special situations, maybe you have rational functions in several variables, maybe we have refinements, maybe we have situations that just don't allow this, but rationality is a good thing for everyone who's interested in doing explicit computations. Yeah? What is a rational function? It's a quotient of two polynomials. So there's a hope to write this down in the sense of writing down finite information that encodes all of this. Yeah? If I just get a sequence of numbers like this, I don't know when to stop searching for more data. If I have a result that says the generating function for this information is an Euler product of rational functions, then I have a chance to learn or to find out something about the rational functions that I need here, get some control over the degrees of the numerator and denominator, and then say something about the linear recurrence relations that the rationality here asserts, at least for the local situation. So there's a challenge there's a challenge to compute these rational functions. And again, I put an inverted comma around this because computing means different things to different people, and even to the same people it means different things at different times. Computing might mean that you take out your pen and paper and you compute it. It might also mean that you design software and implement it in a computer, which then computes things. And Tobias Rossmann has done this, and he will tell us lots about the theory and the practice of software that he's written and is maintaining to do this in many interesting examples. Yeah, so general themes that I find particularly exciting, I highlighted 3. The first one is combinatorial Denef formulae. Combinatorial Denef formulae. Formulae for what? Well, I just said these Euler factors are often rational functions. So these rational functions, they have a finite expression. And yeah, often, without going into details what that means, these local factors have particularly pleasing expressions, and now we're certainly entering the realms of combinatorics. Often, that's a heuristic or an observation, or just a consequence of my personal style, I don't know. Often, these local factors can be written as finite sums. I index here by this prime. Yeah, I mean, everything here so far, we had infinite amount of information. This is a finite sum indexed by flags in posets. So I leave precise definitions for later. So for me, P is a finite poset, just a finite set with a partial ordering on it. O is the order complex of this poset, and elements of this order complex are just flags, sequences of elements, one contained in the next. Yeah? Such a flag has, yeah, I can write down as y1 less or equal to y2 less or equal to up to some length yl. Yeah, so the yi's are elements in the poset, and I just chose some of which contain each other, so to speak. Yeah, objects like this I will call flags. Combinatorialists call flags. Anyhow, what do we do for each flag? Well, for each flag, we have a product of geometric progressions, one for each element in this flag. And we have a very simple looking rational function, pretty much looking like the local factor in this Euler product. Here it was 1 over 1 minus the variable. I have products of the form x over 1 minus x, and I write xy to indicate that I'm not stingy with variables. Yeah? So there's one variable for each element in this poset. Okay, I'm not stingy with variables, but I'm also not hesitant to then substitute for these variables certain monomial expressions. So for xy, I then substitute something like p to the ay minus bys for certain numbers ay in n naught and by in n. And if you follow me again on the left board, you see that this is exactly, well, almost exactly, if you discount the numerator, what we did in the subgroup growth zeta function of z to the n. Yeah, so we had here 1 over 1 minus x1, 1 minus x2, 1 minus x3, 1 minus x d minus 1, so to speak, for xi substituted by certain monomials in the variables. And that's something that often happens, and I left some space here. I left some space here for a weight, so to speak, and that is what makes these formulae combinatorial. So I have often functions phi f of p to the minus 1. And these functions phi f in this case are, let me say, combinatorially defined polynomials. Combinatorially defined polynomials. And rather than spending our time on defining what a combinatorially defined polynomial is, let me give you one and then appeal to your flexibility to think what a more general family of such polynomials might be. Let me clear some space to give you, if not a proof of this proposition, then an alternative way of writing this Euler factor as a combinatorial Denef formula. In this way, I will be able to introduce a family of combinatorially defined polynomials that you might recognize as such. So here's a fact, not easy, not hard to prove. And this fact says that this local factor of the subgroup zeta function of z to the d is given by a combinatorial Denef formula. So this zeta function of z to the d at the prime p, which is what's written here, I can also write as a sum of indexed by subsets of the integers from 1 to d, for which I use combinatorial shorthand d with square brackets. And now here I have a product for each element in the flag. I equals I, and I. And here I write xi over 1 minus xi where. So I have to tell you something about how I substitute these variables. For xi, I substitute p to the n minus I minus s all to the I. What this precisely is not so important. What's important to me now is the shape of this formula. So it's a sum, it's a finite sum indexed by flags in the poset of integers 1 through to n ordered naturally. That's nothing else than a subset. And as combinatorially defined polynomial, I have the multinomial coefficient d over I evaluated at p to the minus 1. So let's have a look at this. So this is the, if you wish, p inverse multinomial coefficient. N is d, always, yes. N is d. N is d. D is nothing to do with this index. Yeah? Okay. So the multinomial coefficient d over I is really a polynomial in a variable y, which I later substitute with p inverse. And it's defined in the following way. I is a subset of 1 to d. Allow me to give names to its elements. So I is a set of elements I1 through to IL, say. And with this definition, I can define what d over I should be. That's d over IL, y IL over IL minus 1, y, and so on down to I2 over I1, y. And A over B, y is just the usual y binomial coefficient. And that has a Wikipedia page, so I can stop here. Yeah? The point, sorry? What's the power of xi is p to the d minus I minus s to the I. Yeah? I know it has a Wikipedia page because I looked it up last night, and the Wikipedia page tells you something very important about this quantity. So here we substituted P inverse in it. Maybe some eyebrows were raised. I mean, we are counting stuff, yeah? Why should I invert primes? Well, you should do it if you do the exercise of proving that this is correct, and then you will see that these fractions of P get cancelled with powers of P later. But if you do, and I suggest you do, you follow me by substituting for Y not P inverse but P, you get, you evaluate this polynomial at a prime number, and what you get is a quantity that has a geometric meaning. So here's a fact. You get lots of facts from me, sorry. Fact, if P is a prime, then D over I evaluated at P is something geometric, namely it's the number of flags of subspaces of the finite vector space Fp to the D of dimension type I, by which I mean that each member here, Vi, has dimension I. Dimension Vi is I. Yeah? Number of linear subspaces of Fp to the D with prescribed dimensions, this quantity is given by this polynomial. So, and that connects the leftmost board with the rightmost board, I reckon. So I said here what I mean by, well, I indicated what one might mean by combinatorial Denef formulae, namely sums of this form where these polynomials had a combinatorial definition. Actually, I also gave you a geometric reason to care about these numbers. And by telling the story in this direction, I'm in a way reversing the historical developments. So I call these Denef formulae because it was Jan Denef, algebraic geometer from Leuven, who told us how to express local zeta functions like this as sums like this with coefficients which were very much of an algebro-geometric origin, namely counting points on algebraic varieties. And in a way, what we are doing here in combinatorial defined, in combinatorial Denef formulae, we concentrate on Denef formulae where these polynomials count numbers of Fp rational points of varieties, but which have a combinatorial flavor, without getting into what that might mean. I mean, you agree that flag varieties have a combinatorial flavor. You might agree that Schubert varieties have a combinatorial flavor. You might agree that toric varieties have a geometric flavor, yeah? So this is a connection I wanted to indicate. Okay, theme A is one of three. Let's see whether we find space and time for the other two. Theme B, that pervades many pieces of work in this area, is reciprocity or self-reciprocity. I said, and didn't rub off yet, the meta theorem that local zeta functions solving problems in enumerative algebra often are rational functions. Rational functions as quotients of two polynomials often enjoy a curious kind of symmetry. And this symmetry, let me just write down a slogan for this. inverting the prime p is, in effect, inverting also this variable t. Yeah? So if I write p to the minus s and then I invert p, then I invert t. But I also mean inverting the prime p in any coefficients that these rational functions have, which is an obvious thing to interpret if these coefficients are polynomials in p and can be done in other contexts. Anyway, when I play with these functions and I invert the prime p, more often than not, but not always, we get back actually the original functions. Up to some constants, which I don't want to bother naming too extensively. This is something that people in combinatorial geometry observed and studied intensively. This is a kind of duality or self-duality property. And the precise reason, so to speak, for these kind of self-reciprocity phenomena vary a lot, which from my point of view just means that we don't have a unifying theory yet for what we are actually being told here. So there's a famous book by Richard Stanley. Some people just call it the Green Book if they can't remember the title. What's the title? Commutative Algebra. Combinatorics and Commutative Algebra. Is that the title? Anyhow, it's a book that in the 1980s told the world that certain combinatorial enumeration problems really should be looked at with a toolbox from commutative algebra. So he explained that certain generating functions that people studied were really Hilbert series of graded algebras, and in this case, or in this world, reciprocity phenomena like this reflect Gorenstein properties of associated rings or modules. Whatever that is, it's an exciting bridge between purely combinatorial looking reciprocity phenomena on the one hand and algebra on the other hand. I would be glad if I could say something that tied together theme A, theme B, and theme C with the topics of the lecture courses that await you in this week. I already told you that Josh is about to tell you something about lattices and lattice counting functions. I already told you that Tobias will tell us something about the theory and practice of computing zeta functions coming from module enumeration problems. I have told you that one of the very motivations of refining well-known generating functions like this comes from our interest in the subgroup structure of finite abelian p groups. And Amri will tell us something about the enumerative theory of subgroups of finite abelian p groups and how it connects to the theory of symmetric functions. What I haven't told you yet, well, it's on the board, but I haven't made the connection with what Angela will tell us. Well, Angela will tell us about permutation statistics, won't she? They're not on the board yet, but implicitly they are. So I said something about the Wikipedia page of multinomial coefficients, didn't I? I said that di at a prime p counts something. Now, I hope that the Wikipedia page also tells you something about an interpretation of the multinomial coefficient diy in terms of permutation statistics. And if the Wikipedia page doesn't, then Stanley's enumerative combinatorics will do. So this polynomial here, this is another fun fact. It's a polynomial with non-negative coefficients, which is surprising in itself, I reckon, before you think about this. And well, while you're at it, you might actually find a reason for these non-negative coefficients. For example, if you connect this with the cohomology of flag varieties. But even without doing this, you might discover that this polynomial has a description in terms of the length function on the symmetric group of degree d. No d is equal to n, right? So this is this d here. So if you run over all elements in the symmetric group d whose descent set is contained in I, yeah, so the descent, Angela will remind us or tell us what the descent set of a permutation is. If you run over this descent class and for each element in here harvest y to the L of w, where L is the Coxeter length, the length of a shortest element, the length of a shortest word representing w as a product of Coxeter generators, arguably one of the most celebrated Weil group statistics there is, you have a connection between such combinatorially defined length functions and the kind of combinatorially defined polynomials that we see in combinatorial Denef formulae. Time is pressing, and I want theme C at least on the board, because it's in a way maybe I think it's a very promising theme where lots stays to be discovered. Let me call theme C special values. Special values of zeta and L functions are, of course, celebrated topic in number theory and algebraic geometry. And I think we are just seeing the tip of the iceberg of special values of zeta functions in enumerative algebra. Let me tell you something about two specific special values that have surfaced in recent years and kept research active. The first one is, so Benjamin will tell you presumably about representation zeta functions of groups. So he will tell you something about zeta functions that enumerate the irreducible representations of a group G by degree. So he will maybe write down sums that resemble this one. So here I run over all the irreducible characters of a group G, and I weigh them by their degree, and I raise that to the minus s. And if I'm lucky, there's a theory that says that this makes sense, and this yields a somewhere convergent Dirichlet series. And if you do this for a finite group, then it's a simple exercise, I reckon, in second year algebra, that the special value at s equals -2. So if I take these characters and I take their squares, I just get the size of the group. What's remarkable is that there's a theorem that says that this, in some sense, this is true for groups, well, for infinite groups. So there's a theorem by Witten, Sapirain, Ben Klopsch, and John Gonzalez Sanchez, that says for some infinite G, and these are compact p-adic analytic groups, the special value at s equals -2 is 0. And I find this remarkable in many ways. -2 is certainly not a value of S for which this series converges if there is an infinitude of summands here. Yeah? So this is a statement about a special value of a zeta function outside its domain of convergence. Really remarkable, I find. There is another indicator that there is lots yet to learn for us about analytic properties, if you wish, of such groups. So Tobias might tell you about submodule zeta functions. That's the second pointer I want to give in this direction of special values, two of many that we could discuss in this week. Okay, let's just grab a bunch of matrices. Let's grab an algebra of n by n matrices over Z and think of them as operators on, no n is D, right? So this is D by D matrices. Let's think of them as acting on Z to the D in the natural way. So A acts on Z to the D. And now let's do the same thing that we did over here. Let's run over all subgroups of Z to the D, of all submodules of Z to the D, but not all of them, but only those which are invariant under this algebra of endomorphisms. So let's look at the submodule zeta function associated with this bunch of matrices. That's the Dirichlet type zeta function running over all subgroups of Z to the D, submodules of Z to the D, which are invariant under A. This, by the same general principles, is a product of local such objects, which, by the same general principles that I didn't say anything about, are rational functions in P to the minus S. So they are meromorphic functions somehow trivially. They have a domain of convergence somewhere on some right half plane. But if you look at examples of them, for example, if you look at the huge database of such functions that we have now, thanks to Tobias' zeta package, well, Tobias made observations about these local zeta functions. So he formulated a conjecture that says the following. Maybe I can take that much space and that much time. If A is nilpotent, as it was, for example, in the case over here, yeah? I mean, counting all sublattices is the same as counting all sublattices invariant under 0. Yeah, but in general, you might take some nilpotent subalgebra of the D by D matrices. You get Euler product of rational functions. Tobias observed that these rational functions all have one thing in common. Well, two things they have in common. They all have a pole at 1. At t equals 1, s equals 0. So this factor 1 minus t you see here for the abelian case, but heuristically you see it in all examples that people computed. And what's more, if you look at the residue of this pole, it's always the same. You can see what it is. It's 1 minus p, 1 minus p squared, 1 minus p to the d minus 1 inverted. So this residue, Tobias observed in examples and conjectures in general, is independent of the algebra structure. So in concise terms, if you take the zeta function, the submodule zeta function of this nilpotent algebra of endomorphisms at the prime P, and you divide it by the same thing for the zero algebra, the object that we called the P's local factor of the zeta function of Z to the D, and you evaluate it at s equals 0, you always get 1. This is a concise way of saying that this residue doesn't depend on the nilpotent algebra, which is hugely surprising. We haven't had time to discuss it here now, but these rational functions, they become very complicated. They don't tell algebras apart, but they get very complicated. And they should have the same behavior at a specific value in a huge class of zeta functions is highly remarkable. Right, I could have told you more about special values. I could have told you much more. I could have given a course, I reckon. I could have told you, for example, more about these connections with commutative algebra, with Hilbert series of graded rings and modules, but I reckon I don't, because my time is up. Your patience with me should be over by now. I thank you for your energy so far.
Do you insist on uniformity?
In a way, the uniformity in P is built into that term, right? Because I, in a way, postulated the phi f's to be polynomials. Yeah, I mean, you're hinting.
Independent of P also. So this degree depends on P.
They are integral or rational polynomials in P or P inverse.
Right, but here independent of P, there's a degree, right?
Here, in both cases, the coefficients are polynomials in P with integer coefficients which are independent of P. Yeah, but you're hinting, of course, at the fact well known by now that in general Genève formulae, these point counting functions, they can be very wild indeed. Yeah, and that's in a way we are cornering here the wild world of Genève land in an interesting combinatorial land. Yeah.
Small question. Say that this PB is more like Poincaré duality.
Yeah. Sorry?
Yeah, just that it's like Poincaré duality.
It should be a Poincaré duality, but in what cohomology theory? I don't know, but yeah, exactly. Yeah. Very well.
What class of groups did you study?
Aha. Well, why don't I pass this question on to Benjamin? You're most likely to talk about representation in zeta functions, no?
Which class of groups?
For which class of groups will we care about representation in zeta functions?
This week?
Yeah.
We'll look at chaotic analytic groups and possibly applications for arithmetic groups. I'm not sure we'll get very far.
Okay, so p-adic analytic groups connected with arithmetic groups makes me think, Benjamin, correct me if I'm off the path of virtue. So things like SL, not N, not D, capital N, Z, or ZP for the p-adic integers. Yeah, groups like this. Very good. As I'm chairing and policing myself, I should chair and police myself and hand over to Benjamin.